And then we've got 2 minus negative 4. So that's like 2 plus 4, which is 6. And then now we've got 9 minus negative 10. So that'll be like 9 plus 10, right? So that'll be 19. Okay, so that'll be the new version of the first row. Now for the second row, it's going to be replaced with row 2 minus 2 row 3. So let's do that entry by entry. So we're going to have 0 minus 2 times 0. So that won't change. That'll still be a 0. We've got 2 minus 2 times 1. So that's 2 minus 2, which is 0. Of course, that's actually why we chose this operation, was to make that a 0. And then now what will we have? We'll have negative 7 minus 2 times negative 4. So that's actually like negative 7 plus 8. Right? So that's actually going to be negative 7 plus 8 will be 1. And then what will happen when we go negative 17 minus 2 times negative 10. So we'll do that. That'll be like negative 17 minus 2 times negative 10. That's going to be like minus negative 20. So in other words, that's the same as negative 17 plus 20. So you'll actually end up with a 3 here. So that'll be our new version. And you can see, if I were to just scroll down and just let you take a look at all of the matrices. Now notice that as we start at the top and we slowly move our way down, we're getting more and more zeros on this left-hand section. That's what you're trying to do. That's the goal here. So the first two columns are looking great. The third column, we're going to do a couple more operations. We're going to turn this 6 into a 0, and then we're going to turn this negative 4 into a 0. And these are the operations that are going to make that happen. We're going to take row 1, and we're going to replace it with row 1 minus 6 times row 2. And then we're going to take row 3 and replace it with row 3 plus 4 times row 2. And that'll have the effect of making both of these zeros. So let's carefully follow it through and see what happens. So in this time, it's row 2 that's not changing. So let's start with row 2. We know that row 2 is going to be 0, 0, 1, 3. And then now we can fill in row 1 and row 3. So row 1 is going to be row 1 minus 6 row 2. So if we do that entry by entry, we're going to have 1 minus 6 times 0. Well, that's just 1 minus 0, which is going to be 1. 0 minus 6 times 0, still going to just be 0. Here we'll have 6 minus 6 times 1. So that's going to be 6 minus 6. And that's why that'll end up being a 0. And then we have 19 minus 6 times 3. So you've got 19 minus 18, which is 1. And that's the first row. Now the third row, remember we're going row 3 plus 4 times row 2. So we're going to add row 2 to row 3 4 times. So we're going to have 0 plus 4 times 0 is still going to be 0. 1 plus 4 times 0, that's just going to be 1 plus 0. Now we have negative 4 plus 4 times 1. That's like negative 4 plus positive 4, which is going to cancel out and give you 0. And then now here, what do we have? Negative 10 plus 4 times 3. That's negative 10 plus 12, which is 2. Okay, so that's pretty good. We got a lot of zeros here, and what isn't a 0 is still a 1. That's part of what we're trying to do. One more step I'm going to take here, though, before we use this to extract the answer, is I'm going to interchange rows 2 and row 3, just so I can show you the notation that you would use to do that. So I'm going to take row 2, and I'm going to interchange it with row 3. So you can see what I've done is I've drawn just a double-headed arrow there. And that's what that means. That means interchange the two rows. So what that's going to look like, the first row won't change. 1, 0, 0, 1. And the second row will be, oops. The second row is actually going to be the third row from our original matrix. It's going to be 0, 1, 0, 2. And then our third row is going to be our old second row. So it's going to be 0, 0, 1, 3. Okay, so that's about as good as you can do. By the way, this is a perfect example of why I highly recommend using pencil for doing these problems. It's really easy to make one accidental mark and then it's easy. It's hard to read your work. Unfortunately, if I use pencil on these videos, it'll make the mathematics it won't show up very well on the screen. So my hands are tied, but I don't recommend following my example. I really recommend that you use pencil when you're doing these problems, because errors are just going to happen all the time, unfortunately, and it can be really frustrating if you don't have a way to fix them and keep your work clean and organized. Things get frustrating really quickly otherwise. So I really, really can't stress this enough. I really recommend using pencil. I've seen lots of people try to use pen, and it works okay sometimes, but sometimes it just creates a lot of needless frustration. So that's my suggestion to you. But let's go back to this problem now. Why is this good? Why do we shoot for this? Well, remember the context. Let me slide this down just a bit and go back up to our original setting. What were we originally looking at? We were originally looking at this system, right? Remember, that's what this augmented matrix came from. It was the augmented matrix, or sometimes called the coefficient matrix, of this equation up here, or this system of equations up here. So we just picked off all the coefficients, all the constant terms, and put them together into this augmented matrix. Well, now what would happen if we did the opposite down here? So down at our last step, what if we said, okay, instead of looking at this as an augmented matrix, what if I said, well, convert it back to a system of equations? What system of equations would you get if you converted this to a system? Well, if you remember that the variables that we used in the problem were x, y, and z, just convert each one of those equations to, or each one of these rows to an equation. So this will be our coefficient for x, this will be our coefficient for y, this will be our coefficient for z, and this will be our constant term for the first equation. So I'd have 1 times x plus 0 times y plus 0 times z is equal to 1. That's what the first equation would be. And this would, I'd have 0x for the second row plus 1 times y plus 0 times z is equal to 2. And then for the third row, I'm going to have 0 times x plus 0 times y plus 1 times z is equal to 3. This is the system of equations that corresponds to this augmented matrix. So let me write that down. This is the augmented matrix of this system. And then now, if you move your attention over to this system, you look at this and think, man, that's a really weird way to write these equations. If I asked you if there's any way to write this in a simpler manner that would involve less symbols, you'd probably notice that, hey, well, first of all, just at every single term, there seems to be more written than needs to be. 1 times x, why not just write x? So this could just be written as x. And then if I go x plus 0y plus 0z, these terms are both 0 anyway. So I'm really just saying x plus 0 plus 0. So really the whole left-hand side of this equation is just going to be x. So let's write that instead. Let's just go x equals 1. That's really what the first equation says, right? In the second equation, similarly, you've got 0x plus 1y plus 0z. This whole left-hand side just evaluates to y. So you've got y equals 2. And then the last equation, the left-hand side of the equation, everything just evaluates to z, because you've got 0 plus 1 times z. That's just going to be z equals 3. So this is actually the system of equations that corresponds to this augmented matrix. And this system of equations, there's something nice about it. There's no work to be done. It's immediately solved. The solution to this system of equations is right in your face, right? It's almost as if this system of equations is just literally telling you what its solution is by the way it was written down. And that's exactly true. So that's how this process works. You just keep working, applying steps to the augmented matrix to make it simpler and simpler until the solution just pops off the page. So our final solution then, let's write it down here. The solution, let's write it in point form like we did last time. The solution is given by, our point now is going to have 3 coordinates for the variables, and then for the solution, the actual values, we're going to have the 3 coordinates, 1, 2, and 3. So that's our final solution to this system. So that's the manner or the method that we'll use to solve systems of equations in this course. And the nice thing about this method is that it scales nicely. As you get more and more complex problems, the amount of steps required and the number of calculations required to do this process stays relatively under control. But if you were going to use the substitution method to solve a system of equations, that gets very unmanageable as the number of equations and number of variables grows. If you were to say have a system of 10 equations and 10 variables, this process, it would still be a lot of work no matter what you did, but this process that we did here, you could use this process and it would still be reasonably efficient. So that's one of the reasons we like this method. So that's what we'll use in this course.